So we discussed how and what matrix inversion means geometrically. Now let's come down to the numerical implementation aspect of it, and how do we implement it numerically, and how do we find out the inversion of a matrix is what we want to discuss, right? So the matrix inversion numerically is given by this equation where M inverse is equal to 1 divided by determinant of the original matrix M multiplied by adjugate or adjoint of M. Okay. We have dealt with determinant of a given matrix, but we have not dealt with adjoint or adjugate of a matrix. So let's go through some concept what this adjoint and adjugate means and how do we compute it. In order for us to do this, we need to first define what is cofactor, what are the minor of the matrices. So we need to go through a couple of other operations on matrices which we will cover through this example problem. Okay. Now, first thing is, in order to do the inversion, we need two component determinant of the matrix, and we need to do the adjoint or the adjugate of the matrix. Now, what is adjugate of a given matrix? It's essentially a transpose of the cofactor matrix of M. What is the cofactor matrix of M? Which is given by this equation where Aij's are essentially minor of a matrix M. Okay, so I know that this seems a lot of involved and there are a lot of component to it, but let's go through a simple example problem where we are going to discuss each of these elements separately, and then we will also take a system of equation and try to solve that equation using the M inverse. So let's first focus on matrix inversion and a numerical example that goes through how to calculate adjoint, determinant, cofactor, and matrix minor of the matrices which are involved in computing the inverses. Okay, so let's discuss this example. So we have this mx equal to v. So what we want to do in order to solve this, we need to invert this matrix. So x is going to be equal to inverse of this matrix. So how do I take this matrix and invert it, and what this inversion of this matrix mean and how to numerically implement is the focus that we are going to do. So as I said, in order to compute this, you will need two things. One thing is basically the determinant of this matrix, and the second is the adjugate or the adjoint of that matrix. So let's see how do we do that. Okay, remember, determinant is in denominator and adjoint is in the numerator of this equation. So let's calculate that. Okay, so first component is we take the matrix M, we take the determinant of that matrix. So if you recall, the matrix was this matrix. I take the determinant of that matrix. So determinant of this matrix is going to be some value, and we know how to compute the determinant. We have already discussed this aspect previously. So using the equation we can compute this, and that will give me the overall determinant of this matrix. So that comes out to be minus 62. So that gives me the denominator of this equation. Now we need to focus on the second component that is involved in the M inverse computation, which is the adjoint or the adjugate of this matrix that we have, right? So let's start with, first of all, understanding minor, then understanding cofactor, and then understanding the adjugate, because we need to backtrack and go in the reverse order to first begin with the minor of a matrix, then compute the cofactor, and then go to the adjugate. So minor of a matrix Aij is determinant of a submatrix formed by deleting ith row and jth column. Let's understand this, what it means. So if I have a matrix M and if I want to compute minor A11, what I'm going to do is I'm going to first form a submatrix by deleting the ith row and jth column. And in case of A11, ith row is first row and first column. Okay, so if I take this, I will delete first row and then I will delete first column. And here we will arrive at this submatrix. Okay, and if I take those components, which is 2, 0 and 0, 7, and take a determinant of that, that gives me the A11 component. Okay, so if I carry that out, the determinant of 2, 0, 0, 7, that will be 14. So A11 will be equal to 14. Now, how many minors we will have? We will have as many minors as the number of element in the original matrix. So the second step should focus on moving from 1, 1, 1 and computing what it would be 1, 2. So let's go through that calculation too to understand how the process is working. So if I take A12, right, this is the second minor that I need to compute. So what I'm going to be deleting? I am going to be deleting the first row and the second column, right? If I take this matrix, the first row is this one and the second column is this one, right? So I take this one and eliminate that, and that will leave me 9, 11 and 0, 7. And so 9, 11 and 0, 7 is going to be, let me write it here so that you can see it clearly. Right. So if I eliminate this row and this column, then we'll have 9, 11, 0, 7. So, the determinant of 9, 11 and 0, 7 will be essentially this value that is there. So that is what is computed here. You can see we have 9, 11, 0, and if I take a determinant of that, that will result in 63. So the A12 is going to be 63. Now if I need to move on, I need to compute A13. What we need to do in order to compute the A13? We eliminate the first row and the third column, and this we will have 9, 2 and 11, 0. So that will help us in computing A1, 3. Okay, and if you simplify and solve it, then in that case you will proceeding what we have shown for the first two computation, you will see that that value will come out to be minus 22, and I leave that as an exercise that you can follow. And similarly, you can go on and compute A21. And what is involved in this A21 computation? You eliminate row 2 and column 1. If that's the case, we have 2, minus 1 and 0, 7. So the A21 will be determinant of 2, minus 1, 0, 7. If I take a determinant of that, you can see that 14 minus 0, and that's how we will compute 14. That's how we will get this equation. And so this is how we'll proceed, and we will determine all the minors of this matrix M from A11, A12, A13, A21, A22, A23, A31, A32, and A33. We have 9 elements, and we will have 9 minors of this element, and this is how the minor computations are done. And that is the first step in computing the adjoint of a matrix or the adjugate of the matrix. Once we have computed this minor of the matrix, what we do is we proceed and we compute what is known as, we basically determine a matrix. Let's call that matrix A, where we are listing A11, A12, A13, A21, A22, A23, A31, A32, A33, which are the minor computations that we got from here. So what we did, we took this matrix, we did the minor computation. Now we are taking all this element A11, A12, A13, and using that to construct the matrix A. Okay, so all these elements are now being assembled to compute this matrix A. Okay, so we got this matrix A here, and that is known as the minor Aij of a matrix M. Okay, so this is known as the minor of matrix M. Okay, now from there, in the second step, we compute what is known as the cofactor of M, and cofactor of M is a slightly different version of A, which is given by this equation. So what is done is you take this matrix, okay, and you identify the element that you are interested, and you determine what is the index of that element, and then that helps you in computing this. So let's try to understand what this means. So this one is A11, right? This element is corresponding to element A1, 1. So the ith index of this one is 1, and the jth index of this one is 1. So for this, if I do minus 1 I plus j, right, this is essentially minus 1, since I is 1, 1 plus 1, so this will be minus 1 to the power 2, or this is going to be equal to 1. Okay? So if I substitute this here, the A11 element is going to be multiplied by positive 1. So this value in the cofactor is not going to change. Now let's take the second element and see what is going to happen when we are trying to determine the cofactor matrix from the minor matrix, right? Cofactor is the modified version of a minor matrix, and how do we do that? So now let's take this one, right? This element. This element is A12, right? So what is I? The I is this index. What is J? The J is this index, right? So when I am using this, determine the cofactor here, in this equation we have minus 1 I plus J, okay? So minus 1, I is 1, J is 2, so we have minus 1 to the power 3, and this is going to be equal to minus 1. So what happens here? I will take whatever the element A 1, 2 is and multiply that by minus 1, and that will be the element that I need to have in the cofactor matrix. So essentially this will change sign. From 63 it will become minus 63. Now I will go here, and this I coefficient is 1, the J coefficient is 3, 1 plus 3 is 4, 1 to minus 1 to the power 4 is going to be 1, so this is not going to change sign, and that's how I'm going to be basically using this equation, whether that cofactor is going to have the change sign of element in the A matrix or not is going to be determined by the equation that we have here. Okay, so let's carry this equation, and if you follow this intuition, then you will see that after transformation and after doing this equation, some of the elements of the A matrix are going to be essentially changing the sign. Okay, and you can see the elements that are changing sign is 63, minus 14, 22 and minus 9. Why? Because those indexes, when you take the indexes I plus j, they tend to be odd, and so in that case it basically this will be minus 1, or in other cases I plus j will be even, so this will be 1 and nothing is changed. So this is where you can see the entries that you have where the sum of indexes I plus j is odd, they change sign. So 63 become minus 63, 14 become minus 41, minus 22 become plus 22, and 9 became minus 9 because ij, sum of ij for those entries are essentially odd. Otherwise, for all the remaining, which is like this element 14, minus 22, 32, 2, minus 12, nothing has changed. So from A, we have now arrived to the cofactor. So from the minor matrix, we have arrived to the cofactor matrix using the equations that is given here. So that's the second step. Now what we do is whatever is Cm, we take the transpose of Cm. Okay, so Cm transpose, and that is essentially our adjoint matrix. So once we got this, we will take a transpose. What is the transpose? We will take this column, we will make a row. We'll take this column, make a row. We'll take this column, make a row, and that will give me the transpose of Cm, and that transpose of Cm is essentially the adjoint matrix. So let's show you how that is done. So remember, here the first column is 14, minus 14 and 2. When we are taking transpose, this will become the first row of the transpose Cm transpose matrix, right? So here, when we are computing the adjoint or adjugate, that's the transpose of the cofactor of the matrix M. In the previous one, we computed the cofactor matrix, right? So if you look into this cofactor matrix, 14, minus 14, 2, that should be the first row. 6, minus 63, 32, minus 9, that should be second row. Minus 22, 22, 12, that should be the third row of the transposed, and that transposed is essentially the adjoint. Okay, remember what is this? Adjoint is essentially cofactor matrix transpose. That is equal to adjoint, and this is where from the previous matrix that was shown in the last slide is transposed here, and now that column has become row. Okay, and we get this adjoint. Now what we have done, we have arrived at the numerator, which involved us to compute 3 steps. Minor, from minor we basically computed the cofactor, and then from the cofactor we did a transpose of the cofactor, and those 3 operations allowed us to compute the adjoint or adjugate, which is the numerator of the M inverse computation. And as I already discussed, we already also computed the determinant. Now we have both the determinant of M and the adjoint of M, and we can combine that information to essentially compute the inverse. So remember, the determinant of M came out to be minus 62. So 1 by 62 multiplied by adjoint that we have here it essentially gives me the M inverse formula. So now we will go ahead and multiply all the elements by 1 by inverse 62, and this is the final inverse matrix that we get. And this is the inverse matrix of M, right? And so, you can see that the process is a little bit involved that we are doing, but this is how we arrive at the inversion of a given matrix that is out there.